Now we are going to talk talk about the pi bond. So pi bond consists of two p orbitals that overlap above and below a sigma bond. So a double bond always consists of one sigma bond and one pi bond. So the molecules cannot be twisted without breaking the pi bond. So generally, pi bond is very strong. It's very, very strong, and is stronger than the sigma bond. So that is why to twist a compound with pi bond is very, very difficult. You have to break the pi bond first before you were able to twist a compound. So if you can look at it here, in the case of a pi bond formation, usually you have one pi, when you have p orbitals that is actually remain unhybridized, and another p orbitals that also remain unhybridized. So those two orbitals will now overlap and collide side to side or collaterally or perpendicularly to form a pi bond. So if you have a triple bond, one is sigma bond and the other two are pi bonds. And this is actually as a result of overlap between p orbitals side to sides. So now, in practice, let's practice and see. Draw a diagram to show orbital overlap in sigma and pi bond in molecule of formaldehyde, CH2O. Then state the shape of the molecules and the arrangement of negative charge centers around the central atom. So this is formaldehyde. So remember, in the formaldehyde, we have oxygen, and oxygen have two unpaired electrons, and we have hydrogen. So in this case, we have two lone pair of electrons, of course, in oxygen, and we have sigma bond. So this is our sigma bond. This is our sigma bond, and of course, you have p orbitals. This p is unhybridized, and this one is unhybridized. So they collaterally overlap. To form. So they collaterally overlap to form a pi bond. And it is trigonal planar. It is trigonal in shape. And of course, if you want to know the hybridization of the compound, is simple. You have three atoms that attach to the carbon. You have three atoms that attach to the carbon. So you can because we are talking about oxygen. So it is oxygen. So oxygen is the central atom here. So directly attached to this oxygen is carbon. So it means that we have one atoms. And then, is there any lone pair of electrons in oxygen? Yes, the answer is yes. There are two lone pair of electrons. So you now at 1 plus 2, we have 3. So it means that it is 3 sp2 hybridization. So that means there is one of the p orbitals that remain unhybridized. So it will be used in the formation of the pi bond, and the shape is trigonal planar. That's 3 regions of electron density. There are 3 regions of electron density because it is trigonal planar. Okay. So the next thing now is sp hybridization. So in the case of sp hybridization, we are taking examples with beryllium. So remember, beryllium is an element with atomic number 4, hydrogen, helium, lithium, beryllium, and the atomic number of beryllium is 4. So how are we going to draw the electronic configuration of beryllium? Is simple. We have 1s2, then we have 2s2. And of course, we can have 2p, 0. So it's simple. Since this one and this one have the same energy level, it means that one electron can be transferred from here to here. Then at the end, we are going to have 1s1 in the excited state, and then we have 2s1, meaning that there are only two available bonding sites. There are 2 lone pair of electrons. It means that 2 atoms can be bound together. So when beryllium bond with chlorine, according to valence shell electron pair repulsion theory, it predicts a linear geometry. So it is linear geometry. So 1s orbital hybridized with 1p orbitals to form 2s. So this s and this and this p1 will now hybridize to form 2sp orbitals. So we have 2sp orbitals. And of course, there are two orbitals that remain, there are 2p that remain unhybridized. There are 2p, that is py and pz, remain unhybridized. Okay? So sp hybridization also occur in molecules that contain a triple covalent bond. For example, in acetylene, that is when you have compound like this, acetylene, that is ethyne. There's only one hydrogen here, and also one hydrogen here. So the hybridization of this carbon is sp, and the hybridization of this carbon is also sp. So it means that in this carbon, there are 2p orbitals that is unhybridized, and also 2p orbitals that is also unhybridized. So they collaterally overlap and also overlap. Of course, it has triple bond. So in acetylene, we have triple bond. So this 2p will now hybridize to form 2pi bond. So in a compound like this, if you want to get the number of sigma bond and pi bond, so of course we have 2 pi bond because it has triple bond. So we have 2 pi bond and the number of atoms are 4. So 4 minus 1 is 3. So we have 3 sigma bond. We have 3 sigma bond. So we have 2p unhybridized. So that is why we have 2 sigma bond. So in ethyne, C2H2, each carbon has 2 sp orbitals and 2 unhybridized p orbitals. So the single bond between carbon and hydrogen is a sigma bond, and the triple bond between the carbon atom consists of a sigma bond between 2 sp2 hybridized and 2 pi bonds between the two set of p orbitals. So the 2 pi bonds are in different lengths, 90 degrees to each other, 90 degrees to each other. So a triple bond always consists of 1 sigma bond and 2 pi bond, and the molecule cannot be twisted without breaking the pi bonds. So ladies and gentlemen, thank you all. And this brings us to the end of the concept of hybridization. Till we meet in the next videos.